Okay, so since we are talking about digital circuits and how they're used in computers, let's just think about what is the basic operation necessary in a computer. Think about how a computer works. What is the basic necessary operation, right? There's going to be some kind of input device in a computer, right? You got some kind of input device. Let's say it's a keyboard. So there, I've drawn my pretty computer. So there's going to be some sort of input device, right? So we got an input device, and that's usually an analog device, a keyboard or a microphone or something like that. And then what the computer has to do is it's got to encode it. It's got to encode it as some kind of information that the computer can understand. So I stopped recording for a second, so I need to catch up. I don't remember exactly what I said, but okay, we have an analog input, and so then what does the computer do with that? The analog input might be a microphone, it might be a keyboard, it might be a camera, whatever it is. It's taking a continuous signal, and it's got to do something so the computer can then do something with that signal, right? So what does it have to do? The computer then has to encode the signal. So it's got an encoder. What that does is typically, and it doesn't necessarily have to, but a typical computer will turn that signal into a binary signal, right? It's going to make some kind of binary signal. So that encoder is part of what's inside the computer. It encodes the signal. So then what happens to the encoded signal? The computer, you might use the computer to either save that signal or to manipulate that signal or to do some kind of operations on that signal, right? So we've got some kind of logic or operations that are done, again, in the heart of the computer. We've got the logic and operations that are done by the chips in the computer, by the processors in the computer. So this is what we're going to learn about. We're going to learn about the encoding and the logic of a computer, but also we mentioned that then as well, it's got to save information, it's got to remember information. You got to be able to even turn the computer off and turn it back on again. And so as well as encoding and logic, which are different kinds of operations, we've got a third operation, and that's called memory, right? So you've got encoding, logic, and memory. All of that might happen. There's the memory. It's in the brain of the computer, right? And I would put the processor in the heart of the computer, and the encoder, I guess I put in the bowels of the computer. Doesn't really matter where they go, but that was just for fun. So they're all inside the computer. The memory, or all of these things could theoretically also be an attachment to the outside of the computer, right? An external disk drive of some sort. But those are all part of the computer. Then what comes next after we've taken in a signal, we've done operations on the signal, we have changed the signal, we've saved the signal, then we need to be able to see what we've got, and we have some kind of, we need to send it to our output device, right? So we've got an output device, but we've got to decode the signal before we send it to the output device. The decoding is the same as the encoding, it's just encoding backwards. Those are the same operation. These are the same operation, encoding and decoding. It's just run backwards, right? We're taking a signal, and now we're decoding it and turning it into an analog signal that we can then see on our output device, and we've got some kind of output device like the computer monitor or a speaker where we play music, or any, I don't know, whatever it is that we want to output, whatever signal we want to look at. So those are the operations in a computer. So the three main operations that we're interested in is encoding, decoding, is logic operations, and memory. Those are the three main operations that we're interested in, that we do with circuits, and that's where we're going. So let's start talking about encoding. And if we're going to talk about encoding, we should just define a couple of words. One being bit. I'm sure you've heard the word bit before. Of course you have. And don't know if you knew, but the bit comes from the words binary digit, right? A binary digit is a bit. B for binary, it for digit. And that's the 0 or the 1. So a bit is a single bit of digit. A single bit of information. A single digit of information. So that's a bit, and that's a bit, right? That's 3 bits of information, 0, 1, 0. Okay. So do you know what a byte is? A byte of information is 8 bits. So 8 bits of information makes a byte, and a byte is a typical length of information that might represent a single letter in the alphabet or something like that. We'll see how that works in a second. And then beyond a byte, there is a word. And do you know what a word is? It's typically, and it actually depends, but it's 2 or 4 bytes. Oops, bytes. Oh well. We don't often talk about words much anymore for whatever reason, but what we do talk about is the amount of information that can be saved on a disk drive or the size of a file. Right? We talk about megabytes or gigabytes or even terabytes. So again, I stopped the recording, forget what I was writing, but a megabyte is approximately 10 to the 6th bytes. This is not an important point, but due to historical definitions, a megabyte is sometimes it's a million bytes, sometimes, a million bytes, sometimes it is 1024. Did I do that right? Or sometimes it's 1048 bytes, but it's around approximately a million bytes. It was originally 2 to the 20th bytes, but it is now defined as a million bytes. So it depends who you ask. So in the International Unit of Standards and Measure, I believe that the megabyte is now defined as a million bytes, but originally it was, because we're talking binary, it was 2 to the 20th. There we go, 2 to the 20th. Anyway, and even that's not exact. 2 to the 20th is not exactly 1,048,000. But anyway, a megabyte is about 10 to the 6 bytes. If a byte represents a letter of text approximately, then a megabyte might be a million characters in a text document. If there are 3,000 characters approximately on a page in a text document, then a megabyte would be maybe 300 pages of text. As you know, that things get a lot larger when you get images or video, and that's because it takes a lot more to encode images and video. There's a lot more encoding going on, so it takes a lot more space. Think about, for an image, we're going to talk about encoding now. We're not going to talk about encoding images, but just think about, for an image, if you're trying to encode a single image on a screen, and that screen is, can't quite think of what the size might be, but let's say that it's 1,000 pixels by 1,000 pixels. Yeah, that seems about right. So 1,000 pixels by 1,000 pixels, that's a million pixels on a screen, and you need a color for each pixel, and there's 256 colors. It's going to take you about a byte to encode each pixel. So a single image is about a megabyte, and that's an uncompressed image, right? And that's what you find. Take a picture, look at your phone, and see how much space it takes up. It takes a picture may take a high quality picture may take a megabyte or more. Then you can do various kinds of compression algorithms, and what compression algorithms do is that there's all kinds of things you can do, but you can look at relative color changes from one pixel to another, and instead of saving the actual individual color for each pixel, you can talk about how the color changes from pixel to pixel. So if color doesn't change, it takes up a lot less information. So you can get tricky about the way you save the information in an image, and you can reduce the size of an image using those kinds of compression routines. But in any case, what we're going to do is just talk about basic encoding. And let's just talk about digital to binary encoding, right? Digital to binary. And what I mean by that, binary, is base 10 to base 2. That really is what I mean. So if I have a number in our base 10 system, let's just call that our normal system, right? If I have a number like I am 52 years old, then I want to know how to encode that in just ones and zeros, offs and ons, right? Highs and lows. So that's just taking base 10 to base 2. And you probably know base 2, but let's just go over that a little bit, right? So base 10, for example, it just means that the first digit is the ones place, the second digit to the left is the tens place, the third digit is the hundreds place, the fourth digit is the thousands place, and the fifth digit is the 10,000 place, etc., 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 right? That's base 10. It's just the first digit is 10 to the 0, second digit to the left is 10 to the 1, 10 to the 2, 10 to the 3, etc. So therefore, base 2 must be the first digit is the ones place, the second digit is, or that's 2 to the 0. The second digit must be 2 to the ones place. Third digit must be 2 to the twos place. Fourth digit 2 to the 3. Whoops, this is getting really messy. So there we go, that's better. So you got the 2 to the 0 place, 2 to the 1 place, 2 to the 2 place, etc. as you go to the left of the binary encoding, or the base 2 digit, the base 2 number, I should say. So the first place is the ones place, the twos place, the fours place, the eights place, the 16s place, the 32s place. Just like with base 10, you just take the number of each of those digits you have. Like this, in the case of 52, we've got, oops, let me get a different color. We've got 5 times 10 plus 2 times 1, right? So this is just 5 times 10 plus 2 times 1. But in base 2, we can only have zeros and ones, right? In base 10, you can only have 0 through 9. In base 2, you can only have 0 through 1. So whatever number you have here is going to be that times 1. Whatever number you have here is that times 2. Whatever number you have here is that times 4. But these numbers are only going to be zeros and ones. So how would we represent 52? Well, the way that we would represent 52 is if we had a 1 in this place, that would be 64. So that's too big. So let's go ahead and delete that. Delete the rest of these. As I could put a 1 here, that's 32. So that's 132. What if I add 116 to that? That's 1 times 32 plus 1 times 16. That's 48. What if I add an 8 to that? Plus 1 times 8, that's 56. Oh, that's too much. All right, that's too much. So that's a 0. 0. Where was I? That's 48. So I need 4 more, right, to get to 52. So I went 1, 4. And then I can put a 0, 0. So plus 1 times 4 equals 52. So my age in binary is 00110100. I just added those 2 leading zeros to make it a byte of information. You could just say my age is 1101, right? You could just say this is my age. But I added the 2 zeros to make it a byte of information. It's not terribly important to do, but the reason I do that is because we often encode things into a byte because of when we start using letters and we start encoding letters, we usually use a byte because how many different digits are there in a byte of information? How many different unique combinations can you have in a byte of information? Well, you could have all zeros, and that would be a 0. You could have a 1 in the ones place, and that would be 1. You could have... Okay, so let's just count in binary. Let's figure out how many we can have. We can have 0. That's and let's just now that's with all zeros. And the second line, I'm indicating all zeros, but I'm changing the first bit to a 1. So whereas blank, it's a 0, so I don't have to write them all. So that's the number 1. This would be the number 2 in digital, right? In binary, it's all zeros with a 1 in that place. The number 3, the number 4, the number 5, the number 6, the number 7, right? So I did that quickly, but think about that. Let's say that last one, the number 7, is 1, 4 plus 1, 2 plus 1, 1 is 7. And so you can go ahead and count all the way up to ... the number, whatever this is. Whoops, I went too far. So that's the highest. The lowest is 0, and the highest is 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1. That's those 8 bits. So that equals 255. So that's with all ones. So there are 256 total possibilities because we got to add the zeros, the one with all zeros. So there are 256 possible numbers in a byte. 256 possible numbers represented in a byte. So how do we go ahead now, instead of representing numbers, let's represent letters. Say I want to represent the letter A, or represent the letter B, or represent the word cat, right? So what I have to do, because we're representing it as zeros and ones, is we have to assign a number to each of these. You've probably seen this before, but some of you probably haven't. And so we got to assign a number. So I could just say, oh, let's call A 1, and let's call B 2, and let's call C 3, etc., and Z 26, right? So we can count down and see what T is. And you say, oh, but what about the capital letters? The capital letter is a different letter than a small letter. So if we have 26, so there's 26 small letters that we represent numbers to. We have 26 capital letters that we represent. We need to represent 10 digital digits. We need to represent all the punctuation. Look at your keyboard. 1, 2, 3, 4, 5, 6. Oh, there's about 10, 20-ish. There's about 20 punctuation, etc. And then there's all the special symbols. So ... special symbols. So approximately, if we want to represent a keyboard, we have approximately, let's see, look right here, 52, 62, 72, 82. We have maybe somewhere around 100 and something characters. Well, what we do is we actually leave 256 possible characters. So we represent every letter on a keyboard as one of 256 possible characters. Right, because when you start looking at those special characters that you can do when you're word processing a document or something, you can pick up all kinds of special characters. And sometimes there's even more than 256 actually, there are more than 256 possible characters. But typically, we use approximately 256 different characters, and we assign each of those characters a number. So if T is the 20th, letter in the alphabet, then cat we would encode in digital. In base 10, we would encode that as 3, right? A is a 1, and the T is a 20. 3, 1, 20. But for a computer, we're going to encode that in binary. So we're going to write each of these numbers as a byte. We're going to write each of these numbers as 8 digital bits. So a 3 is a 0, 0, 0, right? 128, 64, 32, 16, 8, 4, 2, 1. That's a 3. That's my first byte of information. Then a 1 is going to be a 0, 0, 0, 0, 0, 0, 0, 1. That's a 1. That's my second byte of information. And a 20 is going to be 0, 128s, 0, 64s, 0, 32s, 116, 0, 8s, because we need a 4 now. Wait, did I do that right? 128, 64, 32, 16, 8, 4, 2, 1. There we go. And so that's 20. That third byte is 20. That third byte represents the number 20 or the letter T. So cat in binary is 000 000 1 0 0 0 0 0 0 0 1 0 0 0 1 0 1 0 0. That's cat. So that's how we go ahead and we encode things like that. That's basically how we encode things that we then therefore send to the computer for processing. The only thing that I should mention is that C is probably not the number 3, and A is not the number 1, and T is not the number 20. That there's actually an international standard called the ASCII standard. There's an international standard so that your computer can understand the same thing as somebody else's computer in another part of the country or another part of the world. We all use the same standard for encoding the keyboard. I'm going to go ahead and just pull up that standard. So here's a standard ASCII table, and I said we're going to represent things as bytes, but you can see here there's only 126 characters represented. I don't know if you can actually see this well on your screen. You could always Google the ASCII standard. ASCII stands for American Standard Code for Information Exchange. American Standard Code for Information Exchange. Anyway, so what you can see here is that the small c is actually digital 99, the small a is 97, and the small t is 116. I'm not going to go ahead and rewrite cat in proper binary, but I would challenge you to. Oh, well, actually, it's already there, right? Cat, here you go. It's 11000011, 11000001, 1110100. There you go. Okay, so that's cat written in binary. So the first part of the lab is building a digital to binary encoder. It's kind of a fun circuit. It's a little bit therapeutic to build. It's a lot of elements, more elements than you're used to. And as long as you are very orderly on your circuit board, it's not too difficult to build. But it takes some time. It takes time to put 30 or 40 elements onto the board and 30 or 40 additional wires. So that's going to take you a little time. But it's a digital to binary encoder. Basically what it does is it allows you to take a digital number. It's got 10 inputs, right? 10 inputs to input a single digit from 0 to 9. And it's going to output the result in binary. It will represent the binary with lights, right? So there's going to be 4 lights because you need 4 bits in order to represent the numbers 0 through 9. And if the first light is lit, that's the number 1. If, let's say, the first 2 lights are lit, that's going to be the number 2 plus 1, that's the number 3. If the first light is lit and the rest are not, let's see. This is 1s, this is 2s, this is 4s, and this is 8s. That's the number 8, etc. So what you're going to show is that if you input a number 0 through 9 by choosing which number, there's going to be 10 inputs. By choosing one of the inputs, then the output will be, the lights are going to give you the output in binary. So that's the first circuit. That's not really how we encode for a computer, because when you're encoding for the computer, you're sending an electrical signal. I guess it's sort of like creating a code for the computer. But the other thing that you have to consider when you're encoding for the computer, you're not encoding every digit at once, like this digital binary encoder is with lights, right? These were your lights turning on. What it actually does is it's got to be sequential, right? It's going to take 1 bit at a time and encode it and send it on to the computer. Take another bit, send it on, take another bit, send it on. We have to do that using what's called a shift register. It's part of the encoding process, and we will talk about shift registers in a later lab. We're going to talk about what we don't do in the beginning when we're talking about binary is the fact that there's a timing issue, right? You got to do one piece of information and then wait for it to be fed to the computer and then do another piece of information, and it's 1 bit at a time. So there is it gets really interesting when you think about, then how fast can we do that? How fast can we send the bits? And that's when we talk about clock speed. That's when we talk about how fast is your computer, right? How fast can it send the bits? Because you can only send it 1 bit at a time. Anyway, that comes up in later labs, not this lab. Okay, the next part of this lab is logic functions. So that's all you need to know about digital binary encoding. The next part of this lab is logic functions. In order for a computer to do anything, to process information, it can only do it logically. That's an important point about computers, that computers can only do logical functions, and so we've got to figure out the building blocks of logic. And the building blocks of logic start with very, very basic functions, and then we will be able to see later how you add functions on top of functions in order to do more complex things. So we're going to start with, for example, if you've heard of logic before, simply things like the and the or function. But then when you learn these basic functions, then you put them all together and you can start turning that into addition and subtraction. You can start turning it into other more complicated logical functions. But let's just talk about logic in general. And this is logic. This isn't necessarily computers. It's logic. You study this in philosophy, logic functions, So this is a widely used concept in mathematics, in physics, in computer science, in philosophy, etc. The concept of logic. So we're switching gears here a little bit. Let's just talk about logic before we talk about the circuits that represent logic. Remember, we're with logic, we're just talking about functions on binary information. So we're just talking about zeros and ones. The first thing is, how do we turn a 0 into a 1? And that's called a NOT gate, right? NOT. It negates what you have. And the opposite of a 0 is a 1, a NOT gate. I just used the word gate, a NOT function. A NOT function takes a 0 input and it makes a 1 output, or it takes a 1 input and it says 0 output. And we call them gates when we're talking about circuitry. They're gates. It's something, it takes an input and it has an output. And by the way, all of these gates will be circuits for us later, and they will be circuits that we can make out of basic diodes, or they can be circuits that once we start to get more complex, we can, just like usual, we can put a bunch of diodes, resistors, and capacitors together and make a better gate, a better NOT function, etc. So these are all going to be circuits for us, but they're general. Right now we're not talking about circuits, we're just talking about the general function itself, and then we'll see how they're circuits. But we call them gates. So the NOT gate has a image that looks like the triangle with the circle on the end, and it's got what's called input and an output. We're going to call the input, we're going to just call it A for that's just going to be what's in the input, and then we've got an output. So we draw these are called truth tables. It's a table that shows what we put on the inputs, and we call it A because we'll start having more than one input, so it's going to be A and B. There's going to be multiple inputs, but there's only one output to a gate. So for the NOT gate, if it's got an input of 0, the output is 1, and if it's got an input of 1, the output is 0. So this is the truth table for a NOT gate. That's what a NOT gate does. That's pretty much the simplest logical function. It just turns a high into a low or a low into a high. Okay. The next sort of most common, actually the next most common one is what's called the NAND gate, but we'll come back to that. Let's start with the AND gate. I did say NAND gate. Let's start with the AND gate. So the AND gate looks like this. It's got two inputs, and it's the AND function. So So we draw the AND gate like that. It's got two inputs, and the output is the AND of the inputs. We say A and B. If A and B are both high, then the output is high. If A and B are both low, then the output is low. But if A and B are not both high, then the output is low. What the truth table looks like for this is if we have A and B, right? I don't know what just happened. If A and B are both low, the output is low. If A and B are not the same, then the output is low. A and B are not the same, the output is low. But if A and B are both high, then the output is high. So basically, really what it means is the output is only going to be high if A and B are both high. The output is only going to be high if A and B are both high. As opposed to the OR gate, which is represented by this symbol, and the OR gate says if A or B is high, the output is high. If A or B is high, the output is high. So if A or B are not high, then the output is low. But if A or B is high, the output is high. If A or B is high, the output is high. If A or B is high, the output is high. It's just if A or B is 5 volts, then the output's going to be 5 volts. with the AND gate, if A and A, in order for the output to be 5 volts, A and B both have to be 5 volts in, right? High. So anyway, there's the AND gate and the OR gate. And the truth tables, right? So what the truth table is showing are just the possible inputs. And the possible inputs are only zeros and ones. There's nothing other than zeros and ones. If there's something else, then the output is indeterminate, if there's something else. And obviously, in real electronics, it's possible for it to be something else. So we define a 0, like I said, as a low voltage and a 1 as a high voltage. And if it's neither a low voltage or high voltage, something in between, the output may be indeterminate. But we'll talk about that later. Okay, so there's the AND gate and the OR gate. Then then we can talk about the NAND gate and the NOR gate. That's not AND, right? Not AND. It's just 2 functions in a row. Right, so the NAND gate is simply the AND gate with a NOT gate. So it's the NOT truth table of the AND gate, right? A, B out, where we had 0, 0 before we had 0, so now we have 1. We had 0, 1 before we had 0, so now we have 1. 1, 0, 1, 1, 1, 0. So what you should notice is that the NAND gate is just the opposite of the AND gate, the outputs, where the outputs were 0 before, they're 1s now. Where the outputs were 1 before, they're 0s now. That's the NAND gate. And actually, the NAND gate, while it can be drawn the way I drew it, it can also be drawn like this. It's simply an AND gate with the dot there. That's the NAND gate. And therefore, you can probably guess what the NOR gate looks like. The NOR gate is, oh gosh, my computer. The NOR gate looks like that. And the NOR gate has a truth table of if A or B are high, then the output is not high, right? The NOR gate. If A or B are high, the output is not high because it's not OR. So 0, 0, if A or B are high, the output is not high. So this is a 1 because A or B are not high, so the OR function would be a 0, so the NOR function would be a 1. 1, 0, 0, 0, 1, 0, 1, 1, 0. This better be the NOT of the OR function that we saw on the previous page, right? There's the OR function right there. So the NOT is just the opposite of that. Okay. I'll just mention there's also the exclusive function, right? So let's say I have an OR gate, and the OR gate looks like that. A, B, out. The OR gate. So just written down the truth table for the OR gate. Right, the possible inputs are all of these, and then this is the output of the OR gate. So now the exclusive OR is slightly different. Okay, so this is OR. Exclusive OR is this gate is drawn with an extra line there. So this is the exclusive OR. I love it, or it's EOR, like the donkey, but spelled differently. It's EOR. Exclusive OR means that if one or the other is high, the output is high, but not both. If one or the other is high, the output is high, but not both. So neither is high, so this is not high. One or the other is high, so the output is high. Sorry, we're looking at 0, 1. 1, 0. One or the other is high, so the output is high. 1, 1. One or the other is high, but not both. They're both high, so the answer is low. So this is the EOR. The EOR output, EOR truth table. So that's basically all of the possible all the logic gates we're going to talk about. You can do all kinds of combinations. You can have a NEOR, a not EOR, and then you can start putting gates together. So let's say, for example, so now let's put some gates together and see slightly other kinds of truth tables. Okay, so what if we had a computer and we wanted to have the computer decide for us instead of us deciding, or how would the truth table be working in our brain? If we said, if anybody in the class wants to cancel class, then we'll cancel class, right? If anybody wants to cancel class, we'll cancel class. If nobody wants to cancel class, we won't cancel class. But if anybody wants to cancel class, we'll cancel class. So that's an OR gate, right? So So if nobody wants to cancel class, if A, let's say A is Dylan and B is Zoe, if neither Dylan nor Zoe want to cancel class, then we're not going to cancel class. But if Dylan wants to cancel class, even if Zoe doesn't, then we'll cancel class. If Zoe wants to cancel class, but if Dylan doesn't want to cancel class, but Zoe does, we'll cancel class. If Zoe and Dylan both want to cancel class, then we'll cancel class. Okay, so if one or the other, if anybody wants to cancel class, we'll cancel class. Only if nobody wants to cancel class will we not cancel class. So that's an OR gate. But that only allows for 2 people to vote. What if we want 4 people to vote? What if there are 4 people in the class? Or what if there are 19 people in the class, right? We've got to have more inputs. So how do we have an input? How do we have more inputs? So then we just cascade. We do what's called, we add up gates, but we cascade gates. We put gates together to create a larger logic function. So here we've got OR gates that are cascaded, and let's see if this is still an OR function, right? We're saying if any one person wants to cancel class, we'll cancel class, but we got 4 people, and then we can add more OR gates if we've got 8 more people, up by whatever, factors of 4 to 8 to 16 to 32, etc. So let's say we've got 4 people, right? We've got Dylan, we got Zoe, we got Leif, and we got Tyreek. Those are our 4 people. And if none of them want to cancel class, 0, 0, 0, then we don't cancel class. But if any one of them, if Zoe, Dylan, whoever, Tyreek does want to cancel class, then we're going to cancel class, etc. So let's go ahead and think about what this truth table should look like. So we actually know that if anybody wants to cancel class, all the outputs should be 1, no matter what combination, as long as there's a 1 somewhere. So let's just think about all the possible combinations, and then let's see if the gate that I've drawn above actually has this truth table. What we want is that if any one person, okay, so I redrew it. Here's my truth table with 4 possible inputs. If there's 4 possible inputs and it's binary, then it's 4 to the 2. That means there's 16. 4 inputs, there's 16 possible combinations, right? 16 possible combinations, so there's 16 rows. This is we want there to be an OR function. If any one of them is 1, then we want the output to be high. If all of them are 0, we want the output to be low. So we can see if this works. We're not going to obviously take the time to test every function. But you can see, for example, let's take this. Let's take this one, for example. A and B, 0 and 1. So if A and B are 0 and 1, 0 and 1, then with the OR function, the output is going to be 1. C and D are 1 and 0, 1 and 0. The OR function, the output is going to be 1. And then 1 or 1 for the next gate, the output's 1, etc. So you can go down the truth table and figure out that the truth table for the circuit drawn, or for the logic gates drawn, is as shown. Let me just go one step further. You can see that if you look at the 2 OR gates, you know that if any one of the inputs in A or B is 1, then you're going to have a 1 as an output for the top gate. If C or D is 1, then you're going to have a 1 for the output on the bottom gate. So if any one of A, B, C, or D is 1, then either this is going to be a 1 or this is going to be a 1 or both. And if one of those are a 1, then the output's going to be 1. So anywhere you have a 1, you're going to have an output of 1. And that's what this truth table shows, that anywhere there's a 1 and an input, you're going to have an output of 1. Okay, so here's an exercise for you. If you would like, you can stop the video right now and think about how would you draw these gates, the A and B or C, and then you think about and you have to pay attention to where the parentheses go. So A and B or C, A and B or C. So go ahead and stop the video, draw those gates. I'm going to show you the solution in 5, 4, 3, 2, 1. Boom. There's the solution for those 2. If you want to study those solutions, you can stop the video. Okay, then I'm going to ask you to draw the truth tables of these. Stop the video, go ahead and try to draw the truth tables, and I'm going to show you the answer in 5, 4, 3, 2, 1. Here are the truth tables for these 2. You can study those truth tables and see if you agree with what I got. Okay, moving right along. But of course, the response to this joke is there are only 11 types of people in the world, those that understand Roman numerals and those who don't. Okay, so let's just talk about now the circuits. We're getting onto the circuits. And in the circuits, we're going to first use diodes in order to build logic gates, but then we will just get IC chips that are better logic gates, right? So there are some issues with logic gates, and that's when you build them, how many can you cascade in a row? It's called fan out. How many gates can, when you have one gate controlling another gate, which controls another gate, the fan out is the number of gates in a row. All right, so this is a fan out of 3. The first gate is controlling 3 more gates. The problem with this in circuits is that each gate is actually going to have a voltage drop. And remember, a high voltage is 5 volts and a low voltage is 0 volts. So eventually the voltage is going to drop too low because, well, we'll see what I mean by this in a second. Let's just say that these gates are made of diodes, right? And so a diode has a 0.7 voltage drop. So if you have 5 volts as an input on this side, then you're going to have a 4.3 volts as an input on that side. Well, 4.3 volts is still close enough to high that it's high, but then you have another voltage drop minus 0.7 volts, and so you've got 3.6 volts on this side. Now is that high or low? And then a 2.9. Now we're getting so at some point you can no longer control another gate if these are, for example, diode gates. Again, remember, a diode has a 0.7 volt voltage drop. So the fan out is the number of gates that one gate can control. So let's just talk a little bit about these voltages and these gates and the limitations. So there are a couple of what are called families of IC gates. So we're going to start by building just regular diode gates, but then we go ahead and just like we did with the timer chip, you can build a timer chip out of from a transistor, but instead, from an op-amp, and you build an op-amp from a transistor. But each time you get more complicated, you just build another chip. So we're going to have chips that are just AND gates, OR gates, etc. By the way, for whatever reason, the most common chip is the NAND gate. But we'll come to that. So those chips, the logic chips that we're going to use once we start using logic chips. They come in different kinds of families that you would use together. There's the TTL type chip and the CMOS type chip, TTL or CMOS. Those are two different families of chips. They've got different characteristics. So theoretically, I guess if you're going to build a computer, you probably want to stick with one or the other, whichever has characteristics that are more like what you want as the specs of your computer. But in any case, the TTL family of chips, they expect a 5-volt input for high and 0 volts for low, but the range, right? There's actually going to be a range which counts as high, and a range which what's happened here? And a range which counts as low, and the range for high is 2 to 5 volts is high, and low is 0 to 0.8 volts. So there's a range in between 0.8 and 2 volts, which is indeterminate. It doesn't, you can't say for sure whether the TTL sees it as high or low, but it should see those ranges that are written as high or low. And then the CMOS family, again, it just has a different range. The CMOS family is, for low, it's 0 to 1.5 volts, and for high, it's 3.5 to 5 volts. For high for the CMOS family of chips. So between 1.5 and 3.5 is indeterminate. Those are just the characteristics of those different types of chips. So you can see for the cascading gates up above, if and they're not. I mean, we said if they were diodes, that's why the voltages would be reduced. But anyway, if it was TTL, you can see that it would be good. 5 volts, 4.3 volts, 3.6 volts, 2.9 volts still is high for the TTL family, right? So the fan out has not gotten to be too much. We don't have too many cascading chips. If it was TTL, if it's CMOS though, you'll see that 3.5 is the lowest voltage is high. So once we get to the 2.9 volts, right, so the fan out would only be 2, right? You can only attach 2 to gates before the third gate has too low a voltage to tell whether it's high or low, right? Because the voltage here is 3.5 volts for high, but we've gone down to 2.9 volts. So if these were CMOS and those were the actual voltages, the fan out would only be 2. And this is not true. This is, for actual CMOS chips, the voltage is not going to drop as you cascade them together. But anyway, okay. So the fan out is the number of chips you can put in a row, the number of chips you can put one after another, logic gates, until the input of the logic gate falls below the high input falls below the limit of what is defined as high. I think I had already mentioned, but what's nice about the TTL family, which is not true about the CMOS family, is that it's powered by a 5-volt power supply, so it expects a 5-volt input. So all of these chips have power, just like the op-amp has power, which is separate from the inputs. So once it's powered by 5 volts, the inputs are simply high or low. It's open circuit or shorted circuit, short to ground. So it's high as an open circuit and short to ground as a low circuit. So the TTL chip, let me pause. So the TTL chip, this is sort of an indication of, so down here where we have ground, that would indicate a low or a 0 input, and here where we have open circuit, right, it's not attached to anything, it's just a wire that's not attached to anything, that would indicate a 1 input, while the chip is powered by 5 volts, right? There's some other input that's a 5-volt power. Whereas with the CMOS chip, the input for high would actually be a 5-volt power supply, and the output for low is still 0 volts or ground. So this is low and this is high. Whoops, didn't mean to do that.